All right, so are we good with this? Problems, questions, concerns? All right, number 12. Somebody came in and said, what was going on with this? Yeah, and I'll be honest with you guys, the first time I read this, I was like, it doesn't even make any sense. But the more I thought about it, the more I thought it made sense. And there's one really important thing that I pulled out of this that I think I wouldn't have thought of if I hadn't done this problem. So it's why I assigned it. I really debated deleting it. All right, so the idea is you've got these position time graphs. So let's focus on this graph for just a minute, okay? And these are crappy graphs because they're not labeled, right? Like you should have a legend, and the legend should tell you what line is what. And that's not happening here. So you sort of have to figure out what the different lines were. All right, so here's what it says. It says the graphs at the right show 4 graphs of position versus time for 2 bodies and their center of mass. Okay, so here there are 3 lines, right? 2 of the lines are for the individual bodies, and 1 of them is for the center of mass. Okay, the 2 bodies form a closed, isolated system and undergo a completely inelastic, one-dimensional collision on an x-axis. So it's a closed and isolated system. What does that mean? No external forces. So what should be true about the velocity of the center of mass? It's got to be constant. Now, this is a position time graph. So how do we represent velocity in a position time graph? The slope, right? Now, if the velocity of the center of mass is constant, that means the slope of the center of mass has to be constant. So the straight line part of each of these graphs has to be the center of mass. Follow? All right? So here, what this is telling me is I've got one object that's got a positive position of, say, 5, and another object that's got a positive position of, say, 2, but a center of mass is 0? Can that happen? You guys see what I'm saying? Your center of mass has got to be between your 2 masses. And this is showing my center of mass position being less than the position of either of the 2 masses. If this is a position of 0, I can't have mass 1 here and mass 2 here, and then my center of mass over here. That doesn't make sense, right? The average position of mass has got to be in the middle. Okay? So D says which ones are impossible. Well, this one totally doesn't make sense. This one doesn't make sense for the same reason, right? So those 2 don't make sense. Are we good with that? All right. Are the other 2 possible?
The lines extend down below the x-axis, or does the
below the time axis? Yeah, I mean they would have to. They've got to be somewhere. Yeah. Yeah, I know. I thought about that too. Like, why didn't they extend this line down? I'm not sure. Show up. Yeah. Okay. So I think graphs 1 and 4 are good, right? Does that make sense? All right. So now, in graph 1, are the 2 bodies in the center of mass moving in positive or negative direction? So the center of mass is clearly moving in a positive direction, and both of my 2 masses, because those are both positive slopes, are moving in a positive direction. So A is positive, B is positive, and then which ones are impossible is 2 and 3. Does that make sense? I think the big takeaway from this, you guys, is that in a closed system, your position time graph has to be a straight line. The position time graph of your center of mass has to be a straight line. That was like that realization was why I assigned this problem. Make sense? All right. Questions on it? I agree that was definitely a weird question, but like I say, I thought there was some value in struggling with it, figuring it out. Okay, so those are all the concepty ones. Any other problems with concepty stuff? Okay, cool. I'm going to jump ahead then and do, I don't know, I mean, nobody, oh, I didn't mean 50, I meant 49. 49 on the list up there?
Yeah.
Oh, good, great. Okay, let's jump ahead and do 49. Because like I said, I've seen problems like this on a couple AP tests, so I think there is, that it's a good idea to do this. Okay, so this is a way that they used to use this method. I don't know if they still do it. I imagine they don't. But they used to use this method to find the velocity of a bullet coming out of a gun. And they would create an inelastic collision between the bullet and a block of wood, and then measure how high this block of wood swings up. All right. So the idea is you've got this. You've got this pendulum. So it's hanging down, and there's a block of wood hanging from it, and the bullet is going to be fired into it. Okay, so the bullet's going to hit the block of wood and embed itself in the wood, and as a result, the block is going to swing up to some position. Make sense? All right. So in this one, here's what we know. We know that the bullet has a mass of bullet is 0.010 kilograms. Notice I converted to kilograms. The pendulum, the mass of the pendulum is 2 kilograms. And then the center of mass of the pendulum rises a vertical distance of 12 centimeters. So we're gaining, what kind of energy is the pendulum gaining? Gravitational potential energy, right? So let's call this, oh shoot, tried to change colors there. Let's call this a height of 0, and we'll call this a height of 0.12 meters. Good? So, why did the problem give us that height? What was the point of getting that height? Yeah, to find the potential energy, right? So where did this potential energy come from? From the kinetic energy that it had down here, right? So the idea is after the collision, the block and bullet system have X amount of kinetic energy. That kinetic energy gets transferred, it swings up, 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 up until it gets to this point, right? Okay, so after the collision, here's what I know. I know that my gravitational potential energy at the top has got to equal the kinetic energy at the bottom, right? So the mass of my system times g times 0.12 meters has got to equal half of the mass of my system times the velocity of the system squared at the bottom. So I guess I should put at the bottom. B for bottom. Follow? So, algebraify this, we can cancel out our m's, multiply by 2, take the square root, and you find that the velocity at the bottom is $49, so you get 1.534, the complete disregard of significant digits. Here's a second. Question?
You were talking about the math of the velocity.
Yeah, I'm not done yet. Okay, so, good though. What did we just find? The velocity of the block of the bullet immediately after the collision, right? Good. So, now for the collision, here's what I know. I know that the total momentum before the collision has got to equal the total momentum after the collision. That means the mass of the bullet times the velocity of the bullet initially, plus the mass of the pendulum times the velocity of the pendulum initially, has got to equal the mass of the bullet times the velocity of the bullet final, plus the mass of the pendulum times the velocity of the pendulum final, right? So let's see, the mass of the bullet was 0.01. I'm going to skip my units because I know everything's going to work out. Everything here is metric. We're looking for the velocity of the bullet initial, as Patrick said. The mass of the pendulum was 2 kilograms. The velocity of the pendulum initially was nothing. That's got to equal the mass of the bullet, which is 0.01, times what's its velocity after the collision? 1.534. Plus the mass of the pendulum, 2 kilograms, times its velocity after the collision, also 1.534. And solve that for the velocity of the bullet initially. This obviously goes away. So simplify, divide by 0.01, and you get the answer of whatever I said it was on the sheet. So you get, it turns out to be like 310 meters a second, something like that. Keeping track of sig digs, it might be like 309 or 312 or somewhere in there. But yeah, Patrick?
Wouldn't it have been easier just to plug the masses that you know in the first formula was? The energy is 0.12,
Oh, I'm so glad you asked this question. That doesn't work. Do you guys know why? He said, why didn't we just, maybe I misunderstood you, Patrick, but what I thought you were asking is, why didn't we set the kinetic energy of the bullet initially equal to the gravitational potential energy at the top? Is that what you're saying? Say it again. It loses energy in the collision. It's an inelastic, completely inelastic collision. So the only way you could do that is if it was an elastic collision. So if the bullet had bounced off of the block without losing total energy, you would have had to have had the. Say again. Yeah. All right, Patrick, does that make sense? Good question. Good question. All right, everybody good? All right, now, so we're going to do a lab like this. The problem with this is no, we've got these little apparatus things that Mr. Brunner bought last year. They're new, like I don't think anybody's ever used them. Well, I'm getting ahead of myself. We can't. I'll talk about it after we do rotational inertia, because otherwise we're not going to. Yeah. All right. So anyway, we're doing a lab that will be similar to this. Okay. All right. So what else was on the list up there?
42 and 44.
42 and 44. Aha. Ooh, this is a good one. I like this one. No numbers. Very AP testy. All right. Okay, so here's the deal with number 42. It says an object with mass m and speed v relative to an observer explodes into two pieces. So you've got this block with a mass m and a velocity v, and it suddenly explodes into two pieces. It says one is 3 times as massive as the other, so it's going to break up. So this is going to be 1/4 of m, and this is going to be 3/4 of m, right? Good. One 3 times as massive as the other. The explosion takes place in deep space. I don't know what that has to do with anything. The less massive piece stops relative to the observer. And we're trying to find, where is it? How much kinetic energy is added to the system during the explosion as measured in the observer's reference frame. Oh shoot, I tacked on an O there. So, what did I do? Yeah, I guess that should have just been V squared, not VO squared, because VO isn't in the original problem. Yeah. Agreed. Okay, so anyway, so we're looking for this. So, all right, so the idea is this. We want to find this final velocity so that we can write an expression for the kinetic energy, right? Follow? Right? But it's tricky because you're really not given that much information, are you? All right? So here's what I know, though. I know that the momentum before the explosion has to equal the momentum after the explosion, right? So that means that m times v has got to equal 1/4 of m times 0, right? Plus 3/4 of m times vf. Follow? Okay, so we can divide everything by m. Okay, and then solve for VF. And you will discover that VF is 4/3 of V. Make sense? Any problems?
Yeah, I got that.
Okay, cool. We're just not done. No, that wasn't. It's not no, good. That's half the battle. All right. So now what we got to do is we got to find our change in kinetic energy, right? Because it says how much kinetic energy is added. So let's find the change in kinetic energy. See what happens. So our change in kinetic energy is, well, let's see. It's final minus initial. So our final momentum should be this. So it's 1/2. Let's see, this thing has a mass of 3/4 m times this velocity squared. 4/3 v quantity squared, right? Let me pause there for a minute. That's a lot to absorb. That's the final momentum of the system. So that is the kinetic energy of this thing right here.
But,
Good? But what?
but minus the initial.
Minus the initial, exactly. So now we got to subtract out the initial. Is everybody good with the final before I subtract out the initial? Okay. So my initial is just 1/2 mv squared, right? Follow?
So it's not the same feet,
Sorry?
but always.
Yes, the full mass and the full velocity. Good. Okay, so now we just got to simplify this. So let's see. So this is 4/3 squared times 3/4. So this 3/4 is going to cancel one of the 4/3, right? Does that make sense? So I'm going to get 1/2 times 4/3 mv squared minus 1/2 mv squared. Follow? Which is the same as 1/2 mv squared times 4/3 minus 1. There are certainly other ways you could have done the math there. 4/3 minus 1 is 1/3. So you get 1/6 mv squared. Cool. Questions with you guys? Alrighty. Let's see. So that was 42. So I think the only other two that are on the list up there are 44 and 57, unless anybody added one.
I had
59? Okay.
44.
Cool. Oh yeah, 59 is a good one too. I actually have 3 stars next to it in my notebook, so that's the most stars that one can get in my starring system. All right. All right. 44. Oh, this one's tedious.
Oh.
Alright.
Can you just tell me how to do it then? Because I thought
No, let's do it because it's got some of the constant acceleration equations that I keep telling you guys you don't know well enough. So I think there's some value in doing it. It'll be a good review of forces and friction and stuff too. So let's do it. It's not that bad. All right. So in the figure, a stationary block explodes into 2 pieces, L and R. So the idea is we're going to have one piece L, one piece R. Presumably the piece L is on the left and piece R is on the right. Right? And they're going to explode this way. So this chunk of the surface is frictionless. And then they slide into these little regions here where there is friction. So there's friction here and there's friction here. Okay? So piece L, so let's do this. So here's what we know for piece L. I know that the mass is 2.0 kilograms. I know that the coefficient of kinetic friction on the left side is 0.40. And I know that it slides a displacement of 0.15 meters. And then I know similar information for piece R, which I'll get to in a second. All right, so why do you think you were given all of this information? Sure, sorry, get yelling. What do you got? Yeah, good, sorry.
Well, the way I did it was a whole lot of just working backwards. You can calculate the force of friction. The force of friction, you can calculate the acceleration.
Yeah.
That you can use.
Let me get caught up to you. I agree with you 100%. So here's the idea. So here's piece L, right? So mass of L, right? So the idea is this is MLG, right? Gravity pulling it down, right? What's wrong?
MLG stands for Major League Gaming.
It totally does. And mass of the left thing times G. All right. Our normal force is ML times G. Now let's see, the block is sliding this way, so I'm going to have kinetic friction going this way, and my kinetic friction is going to be my coefficient times my normal force. Right? Is there anything pushing it this way? What about the explosion? It's already done, right? So now it's just coasting because of inertia or momentum or whatever. Sucker. Hey. No, you're good. She's cheering. Yes, I'm setting her down. Yep, bye. All right. Okay, so, yes, main office. Okay, so this is going to be my net force, right? Follow? So this has got to equal mass times acceleration, right? Oh, so my acceleration is just 0.4 g, right? So the acceleration of the piece on the left is 0.4 g. Good? All right, so why did we find all that, you guys? Alex, what do you got?
I was going to ask a different question.
Oh, I'm sorry, what are you going to ask?
Okay, so I did mine a very convoluted way. Since we knew the displacement for each one, I found the work that friction did.
Ooh, yay, this works too.
It does?
I believe so.
It did for me. I was
Um,
going to ask what
so yeah, if you find the work that friction did, then that tells you the kinetic energy that it started with,
Yeah.
which you should be able to use to find the velocity. So that ought to work. That's cool.
It didn't.
All right, well, let's find the velocity and see if we agree on velocities.
Okay.
All right, so is everybody okay up to here? Okay, so the next thing I want to do is use some kinematics equations to find the velocity that it had at the start of the time it began slowing down, right? So the idea is it's sliding this way with some initial velocity, and then it's going to have a final velocity of 0 after it stops, right? Okay, so we're going to use this guy, yeah, 2AD equals the F squared, so V squared minus VO squared, right? Now, the final velocity is 0, so you get 2 times 0.4 g times d, which is 0.15, equals 0 minus VO squared. I have a mistake, small. Yeah, my acceleration's got to be either my acceleration or my VO. I guess it's not a big deal. Oh yeah, right. Let's see. It's moving this way. The acceleration is that way. So one of these needs to be negative, right? So I guess really the displacement should be negative, right? Cool. All right. So 0.4 times 9.8 is some number, whatever. Solve square root, and your VO for the block on the left turns out to be. Drum roll. What number is this? For negative 1.08 meters a second.
All right, I did.
Good. Everybody good up to that? All right, and then you do the exact same thing for the block on the right, and you'll find that similarly,
Wow.
the velocity initial of the block on the right is positive 1.56 meters a second.
Okay,
Everybody good up to there? It's the exact same process, just you flip everything around and... Okay?
I got all of this stuff.
Yeah, I got both velocities correct, but I still got the mass.
Okay, so Did you get 1.4? Yeah, but it's asking for the mass of the whole thing, so you gotta add the 2 kilograms. Sorry. Yeah, so piece L has a mass of 2 kilograms. Piece R, blah, 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 blah. What was the mass of the block? So you're looking for the initial mass of the block. All right, so, all right, well, we've come this far. Let's finish it. Sorry, Alex. But that's good. Like on an AP test, that would have been 90% of the problem, right? So, yay. All right, so the idea is this. Our total momentum initial has got to equal our total momentum final. Before the explosion, what was our momentum? 0. That's got to equal the momentum of the block on the left plus the momentum of the block on the right. So that's 2 kilograms times negative 1.08 plus the mass of the block on the right times positive 1.56. Solve it. The block on the right ends up having a mass of 1.4 kilograms. So M equals 2 plus 1.4 equals 3.4 kilograms. Cool? All right. And yay for using the work method. That's cool too. I like that a lot. All right. Problems, you guys? Okie dokie. What's next? I think we just have 57 and 59. Is that right? 42, 52, 57, and 59. Alrighty. All right, 57. Come on, computer, work. 57, where are you? There it is. All right. So we've got this ball that's being fired into a barrel of a spring gun. It's initially at rest, so we're going to have a collision here. The ball sticks in the barrel at the point of maximum compression of the spring. Assume the increase in thermal energy due to friction between the ball and the barrel is negligible. A, what was the speed of the spring gun after the ball stops in the barrel? So here's the deal. We've got a ball and a spring gun. Let's see, this guy, the mass of the ball is 0.060 kilograms. And it's got an initial velocity, which they call VI, of 22 meters a second. Based on the drawing, it's this way. So I never do this, but for this problem, let's call this way positive, right? Because everything's going to move that way. So there's no point in keeping track of all our negatives, right? Everybody cool with that? Cool. Let's see. The mass of the gun is 0.240 kilograms. Its initial velocity is 0. And then it's an inelastic collision, right? So it's just 0.240 times 0 plus 0.060 times 22 equals this mass times the final velocity plus this mass times the same final velocity, right? Because they're stuck together. Does that make sense or no? Okay. So we're going to get 0.240 times VF plus 0.060 times VF. You certainly could have combined that in one step if you wanted to. So you get 0.300 VF equals whatever this gives you. Did I write it down? 57. I didn't write it down. Okay, whatever. That gives you some number. And so your VF, if you solve it, ends up being 4.4 meters a second. That away, right? Good? Kurt, are you good? All right. Okay, so we're good? All right, so then B, what fraction of the initial kinetic energy is stored in the spring? Well, so figure out how much kinetic energy you started with.
Yeah, for a fraction.
Oh.
I think it's
You can do that how much?
Sorry? No, you could have given 4/5. That would have been fine. or 8/10 or 80 hundredths would have also been acceptable. Yeah, you're right. I don't know why I give it as a percent. Because I do not believe that it was a. I'm happy to give points if it's a point of confusion. That's not a big deal. All right. I think the V naught thing was a gift. So, all right. Are we good up here?
I really don't like when the process of it, but it's the higher things.
Are you good? Everybody good? Okay, so let's see. Let's find our initial kinetic energy. The initial kinetic energy is 1/2. Oh shoot! It's 1/2 the mass of the bullet times the velocity squared. So the starting kinetic energy turns out to be 14.52 joules. After the collision, your kinetic energy is 1/2 of 0.30 kilograms times 4.4 squared, and that gives you 2.904 joules. So I lost some kinetic energy. Where did it go? Where did it go? It went into potential energy from the spring, right? So just find out how much energy, kinetic energy you lost. That must have been turned into potential energy from the spring. So that gives you 11.616 joules. And so then, just divide. So your fraction, I guess, would be, if you wanted to do fraction, it would be this. Oops. There you go. Fraction. Cool. I'll leave that up to you guys to reduce. Does it turn out to exactly 80%?
Yeah.
Cool. I couldn't remember. All right, everybody good? Questions? Issues? All right. Last one I think was 59. Is that right? 3 stars. All right. So this is another one with a spring. So in the figure, block 1 has a mass of 2 kilograms. So mass 1 is 2 kilograms. It's moving rightward at 10 meters a second. So the velocity of 1 initially is 10 meters a second. Block 2 is 5 kilograms. The velocity of 2 initially is 3 meters a second, also to the right. The surface is frictionless in a spring with a spring constant of 1120 newtons per meter. Let's try to, that's a lowercase k, so you don't get it confused with kinetic energy. Fixed to blocks 2. When the blocks collide, the compression of the spring is maximum at the instant the blocks have the same velocity. Find the maximum compression. So, does that kind of make sense that when they're compressed, that's where they're the same velocity, right? Because what's going to happen is block 1 is going to slow down and speed up block 2, right? Okay? And then eventually, block 2 is going to be moving faster than block 1, right? So that means that you're starting to uncompress the spring, right? Okay? So this was like a gift. That's supposed to be underlined, not crossed out. Okay? You guys should understand that when you've got a collision with a spring, the velocity is the same at maximum compression. That's a good thing to know. Okay? In the same way that, like, knowing that your centripetal acceleration to go around a loop has got to be at least g at the top, right? It's like one of those things that comes up. That's one of them. All right, so we got to find maximum compression. So basically what I want to do is I want to figure out, it says at the instant they have the same velocity. So let's find that velocity, right? So 2 times 10 plus 5 times 3 has got to equal 2 times v plus 5 times v, right? This is the momentum before they collide. This is what the momentums would look like, momenta would look like when they have the same velocity.
Why would it be when they're making
Because block 1 is slowing down and block 2 is speeding up, right? because
But isn't that technically like final velocity?
no, because what's going to happen is they're going to bump into each other. The spring's going to compress for a little bit, and then when it uncompresses, block 2 is going to get pushed ahead. Right?
Okay, yeah.
You see that or no?
Yeah, I get it. Yeah.
So in other words, the problem would continue after this. There's some other final velocity after the
Yeah,
collision.
but I'm just confused as to why that couldn't be the final velocity.
Because we're trying to find the maximum compression. So the moment that we're interested in is the moment when the spring is squished the most, and that occurs when the two velocities are equal.
Okay.
Good? What'd you say, Francis?
The momentum's always conserved. It's not just the initial time, like throughout gets conserved.
Oh, yes. Yeah, very good distinction. Yes, totally. Does that make sense, you guys? Okay. All right, everybody good? All right, so solve this mess. What are we going to get? You get 35, I think, equals 7v. Oh, so that means v is 5 meters a second, right? All right, so now how do I use that to solve the problem? Yes?
So, can you find?
Sorry, I'm not ignoring it. Give me a second.
Never mind.
All right, sure, what do you got?
Oh, well, if you know the initial velocity of the block, you know the final velocity of the block, and you know the spring constant, so you just
I agree with you, but how? Like, I think you're glossing over some.
Find the work that
Yeah, find out how much energy was lost. Right? We lost some kinetic energy before the collision and this moment. So let's figure out how much kinetic energy there was before the collision,
in just one.
how much kinetic energy there is now, and the difference must be elastic potential energy, right, from the spring. Okay?
Would there only be energy loss in block 1 or both?
Well, so block 1 is losing energy, right, because it's slowing down,
Block 2
but block 2 is gaining energy.
Is it block 2 that's gaining energy, or is it the spring that's gaining energy?
Both.
Okay.
Both. Okay, so let's do this. So kinetic energy, block 1, block 2, initial, final. So the kinetic energy of block 1 initially is going to be half of 2 times 10 squared. That's going to be 100 joules. Block 2 is going to be 9 times 2.5 is what, 24.5? No. 22.5. So that means that our total kinetic energy initially is 122.5 joules. Let me double check my notes since I just did that in my head. Make sure, yes, very good. All right, good. So that's the kinetic energy we had before the collision. Now, after the collision, I guess I didn't need to separate it into two chunks now, right? Now I've got a 7 kilogram block moving at 5 meters a second, right? So now my kinetic energy would be 1/2 of 7 kilograms times 5 meters a second squared. So my total kinetic energy final is going to be 25 times 3.5, so 87.5. Follow? Yeah, Alex? Here or here? This is Ki, initial kinetic energy? Oh, 1/2, 7 kilograms. It's 1/2 mv squared. Sorry. Thank you for asking when you didn't read it. Couldn't read it. All right, are we good? So now I can find my change in kinetic energy. Right? So my change in kinetic energy is how much kinetic energy I lost, and it turns out to be negative 35 joules. So, where did it go? The potential energy. So my potential energy must be 35 joules.
Wait.
You sure?
So that change is including the change of kinetic energy from block 1 and block 2.
Yeah, I cheated. I combined my two masses,
Yeah.
but you certainly could have found them individually and then added them, and it gives you the same answer.
So that would mean Is this completely inelastic?
We don't know because we don't know what happens afterwards. But I mean, yeah, the assumption would be yes, because because the idea is, so right now you've got stored energy in the spring, and then as it uncompresses, it's going to get turned back into kinetic energy. So yeah.
So technically, we have no, like, there's no perfect way to tell that all the energy lost to kinetic was gained in the
Correct. Yeah, that's an assumption for sure. Yeah, it's a big assumption to be. Yeah. Well, does it say something about? It says it's frictionless.
That doesn't mean like.
Yeah, I guess like sound and stuff. Yeah. All right. So anyway, so 35 joules equals 1/2 of K. Was K 1140? 1120. Thank you. Times x squared and solve for x. Right? Isn't that what we're trying to find? Yeah. And so you get 0.25. Make sense, you guys? Questions? Okay, cool. So that is that. So we got